Hello. Hello. CS students. Hello, class. Today, we'll be learning about dominating sets. Let's start with a simple example to introduce this concept. We'll consider a small town. We'll call it Algville. Here's a graph representation of Algville. Where each node represents a customer. You are the owner of an ice cream truck company. Summer is about to begin in Algville, and you're anticipating a lot of business. In order to service the whole town, you could place an ice cream truck at every location where a customer is present. However, this is expensive, and you're going to want to optimize the profit you make this summer. This means you'll want to be able to reach all your customers with the fewest amount of trucks possible. So, how can we serve all the customers in Algville without dispatching more ice cream trucks than necessary? Note that each ice cream truck can only service customers that are at adjacent houses to them. Meaning, if an ice cream truck is placed here, it can only service this customer, and this customer. Now, if Algville is a small town, as shown here, then maybe this isn't so hard a problem to solve. For example, one solution could be placing an ice cream truck right in the middle. As we can see with this solution, every customer is adjacent to the ice cream truck. In this case, we have a dominating set of size 1. Please note that this solution is the minimum dominating set. However, there are other possible dominating sets for this graph. For example, another dominating set could be showed like this, with an ice cream truck here and here. Keep in mind that this is not the minimum dominating set, because in this case, we have a dominating set of size 2. Keep in mind that our goal for this problem is to find the minimum dominating set. This is the minimum dominating set for this graph.
In a graph which consists of vertex and edge sets, the dominating set is a subset of the vertex set, where every vertex not in the dominating set is adjacent to a vertex that is. So the domination number, denoted gamma, is the size of the minimal dominating set on the given graph G. Let's examine the dominating set on the complete graph with 5 vertices. In this example, the dominating set can be any subset of the vertex set. At least one vertex is needed because the graph is complete. Therefore, every other vertex is adjacent to any given vertex in the graph. This is a very simple example of a dominating set because only one is needed and every possible edge exists in this graph. What is the dominating set on this graph? As you can see, it isn't obvious, and that is the reason the dominating set problem is considered a combinatorial optimization problem. A combinatorial optimization problem is a problem where you can clearly define a finite number of candidate solutions, or states, and where each candidate solution has a discrete cost associated with it. You can calculate that cost by whatever means is appropriate to the problem. In this case, the states are going to be the vertices in a candidate dominating set. And in this graph, the cost function is going to be the size of every candidate set. The overall aim of a combinatorial optimization problem is to minimize the cost. In this case, we want to find, again, gamma of G, which is the minimal size dominating set. Before we continue, let's look at some more examples. Let's first consider a complete bipartite graph. The dominating set in this case would only require one vertex in each partite class. As you can see, choosing one of each of these to be in the dominating set means that we can reach every vertex. What about in a path graph? In this example, we see that the dominating set needs to include every other vertex in the path. How about a cycle? In an even cycle like this, we see the same condition holds as a path. Every other vertex in the cycle needs to be in the dominating set for it to be minimal. And something similar holds for an odd cycle. In the decision version of the dominating set combinatorial optimization problem, we want to find out, is there a dominating set on the graph that has size at most a given constant? Can you look at this graph and tell me if there's a dominating set with size at most 5? That's an example of the decision version of the problem. So how do we find the dominating set on a given graph? The naive approach would just test every possible subset of vertices. But we know that there are n factorial of those, where n is the number of vertices in the graph. And that is not a scalable solution. So let's try a straightforward greedy algorithm. First, let's enumerate every vertex in the graph by its degree. The next thing we do is if we pick the vertices in the graph with highest degree and add them to our dominating set. This graph has 2 vertices of degree 5. Let's add both of those. What should we take next? Let's add the vertices of degree 4. Do we have a dominating set yet? We haven't been able to reach either of these vertices. So that means let's add this last vertex of degree 3. Now we have a dominating set, which consists of 6 vertices. Here, I've outlined some pseudocode-steps for our previous greedy algorithm for determining a dominating set. The first step we did was to enumerate the degrees of every vertex in the graph. So for a graph with v vertices and e is the edge set, this will take the size of v. The next thing we did was we sorted all of the vertices by their degree. If we apply the quicksort algorithm to this, we can do this in size of v log size of v time. The next thing we need to do is, while we have not made a dominating set in the graph, we need to add the vertex of highest degree from our list from before. Adding a vertex to the dominating set is a constant time step. But the bigger problem is how long will it take to check that our set is dominating or not. One simple way to do it is to iterate through every vertex in your set, and then for each edge on that vertex, mark the other endpoint of the edge as visited. You can do this in size of v times size of e time. We know that the number of edges in a graph is bounded by the number of vertices. Because, for example, in Kn, which is the complete graph on n vertices, has n times n minus 1 over 2 vertices total. So therefore, we know that the size of E is bounded by this quantity. So this means this is going to be in relation to the size of v cubed. And this, because this is on the order of the size of n squared. Therefore, this entire algorithm can take place at approximately size of v cubed time, which is a polynomial time algorithm. However, it should be noted that this algorithm is approximate, not exact. It is not always guaranteed to return the minimal dominating set, because there may be cases where you want to, at one step in the algorithm, pick a worse vertex to add to your dominating set, one with a lower degree in this case. We want to add that to our dominating set in order to have better choices later on in the algorithm. However, because this problem is NP-complete, there is no polynomial time algorithm to determine the minimal dominating set always. Here is an example graph where the greedy algorithm does not produce a minimal dominating set. You can see that the dominating set in this graph are these non-filled in vertices. However, let's run our greedy algorithm from before on this graph first and see where it goes wrong. So the first step, again, was to enumerate the degree of every vertex. Now that we've done that, we see that the degree with maximum vertex in this graph is this one, with degree 5. So naturally, we would want to pick that to be the first vertex in our dominating set. However, we see that this vertex is not in the dominating set, again, composed of these vertices. This is where the greedy algorithm would lead you astray. It would not produce the dominating set in this case that is of minimal size, because the actual dominating set includes this vertex, not this one.